Alright, time for another draftphysics.com, debatephysics.com. Also, still seeking debators, debate-ites, debate-ease, whatever. Somebody else to argue with besides my own, whatever, creation of the arguments of the opposition. Because that's all I can do, is imagine what they might say. But anyway, what you can do. And respond to the videos that are actually out there, but none of them are on the specific subjects. They all evade the real subject, the nature of the thing's function, or they just, tell you a story that has nothing to do with any, evidence. It's just a story they made up. So anyway, made a few videos on the website, so I'll go over those, and then maybe I'll play a little 2-minute crap generic horrible video, and then do some comments if I can find any, and so that's the general outline. So jump ahead as at will and all that kind of crap. Whatever who cares? Do whatever you're gonna do. So anyway, I have the book started in terms of videos. I've got 3 chapters. And I'm sort of debating what the next chapter should be, whether I should go, something a little more detailed on gravity, or continue with what atoms do, but whatever. I'll figure that out. So this one, the first video, is just the force, matter, motion, just explaining that, the real takeaway is that force is something matter collects. And at any one time, it can only collect it in one direction of any dimension. It can't be both going forward and back, because every bit of energy it hits from one side reflects the energy from the other side, or vice versa. So technically it can only have, at any one time, it can only have a direction in a dimension. So it can only have 3 vectors, technically. Whatever, probably. But the point is that it possesses the force, and when it interacts with something else, it's going to exchange what it possesses with what the other thing possesses. They're going to balance their forces, and how much they balance will depend on how long they stay in contact with each other. Pretty much. I mean, that's the way you define it. Alright, so we'll play a little bit of this, and you'll get the idea. In an electron's perspective, the universe essentially looks like it's out to get it. Right, so the simple idea is there's little tiny bits of matter that don't have any motion on their own. They don't do anything on their own. And they're in a sea, a universe full of little golf balls, ping pong balls, whatever you want to think of it as, little indestructible, elastic little bits that never stop moving, and that all you can do is capture them, like birds flying around. You can imagine millions of birds, and some of the birds are heading right towards you, and they hit you, and they're constantly bombarding you with bird pressure. And the fact is you can capture some of them for a period of time, where I got more birds going that way than birds going that way, and I will move in the direction of the birds. But it is a real capture. It's not like they bounce off. They don't bounce off unless you're going against them. Unless you have a bird already going this way, then you lose both the birds. So it's different than the intuitive understanding of how we function in terms of throwing things and activating, making stuff move. It's a little different, the elemental function. But the end result is the same, in the sense that the energy is conserved. And it's conserved because the little bits of energy have to be conserved. You can't destroy them. You can only preoccupy them. You can only catch them for a little period of time, and then you have to release them again. You'll inevitably be required to release them again, kind of thing. Getting into more trouble, and it goes back the other way. And so it's going to end up locked in a magnetically locked. So you can understand that everything is just going to sit there and, by the circumstance of chance of what's coming from one side versus what's coming from the other side. Any one moment it could have a little velocity this way and go a little velocity that way, everything will just end up vibrating in the energy of the universe. That's why you can't get anything to absolute zero, any matter, because there's always this force that you can't get rid of. It'll keep forcing the little bits of matter, the electrons and protons, to react, to act. They don't react, they just act based on what they got hit by. Electron doesn't move. If the electron moves, the field ends up looking like this. So any movement by an object in this sea of ping pong balls, you could understand that, you know, if there's stuff coming this way and I move into the stuff, I'm going to reflect it sooner than it would have been reflected. So if my hand moves towards you, it's reflecting photons sooner than they would have gotten reflected if I didn't move my hand forward. So I'm making a signal in the bird energy, in the fish, in the whatever it is that you, the ether, whatever. I'm making a signal, and every time an electron moves somewhere, it changes what somebody's going to see. And that's how the universe works. It had a shape to account for its polarization. Well, the same is true in this model, in the sense that the photon does... Alright, so that's just the description of the difference between red and blue light. Is, you know, light is just this reflection of energy because electrons are moving. And if they move, they're going to reflect a different universe. Depending on whether they're moving towards you or away from you, you're going to see something different. They have power, like they're creating energy or something. Right, so magnets fool people because, you know, they look like they're doing something. They must be doing something because they're creating this force and this event. But all they're doing is reflecting different. So instead of reflecting purple, they're reflecting blue and red. Something that simple. I really don't go into that much. That was just the closing connection to that phenomenon. I probably mentioned gravity somewhere in here. And that's how the universe... Okay, well, that's a closing statement. So what I guess I was getting to was more the magnetic part, in terms of identifying the fact that there's two types of matter and two types of force. But I didn't think I got into that in the first video, but you know, maybe I did. Anyway, so the second video really focuses on that subject. So we'll play a little of that. I should have checked the audio settings. Yes, I should have done that. Where do I do that? Oh, yeah. Oh, well. This is not going to be that much different. Oh, that's what they all say. Oh, well, who cares what they all say? Isn't that what the whole thing's about? Is you can't trust what they all say. Identified as plus and minus, which is inaccurate. They should be the other way around. Right, so I don't really want to get into making it an opposition argument in these videos. I just want to sort of explain it as if I was a qualified physics instructor and I was just explaining to you what we have figured out. You know, without getting into all the mistakes of made of physics. But it's really hard to do because you want to use some generic terminology like electron, proton. You really don't want to have to explain why we believe those things exist. But anyway, and they did misassign the electron and proton in terms of plus and minus, in the sense that when you do any kind of electrodynamics, the electricity really is about the excess of electrons or the lack of electrons, and that's really what's going to define electricity's motion. And so it's really stupid for electrons to be negative, because the fact is it's adding electrons that creates, you know, positive voltage. But anyway, alright, moving on. The universe, if there is matter, it's going to change what you get hit by. Alright, so yeah, so you could use some sort of Einsteinian statement like, well, the space tells the matter what to do and the matter tells the space where to be, or however they say that crap. Clearly, the force is going to tell the matter what it's going to do, and when the matter does something, it's going to change where the forces are going. So, and that's the yin and yang of the interaction between the two. The charges have no power. All they can do is be a reflection of the forces that hit them. They are just a product of their history as they sit in a field of being exposed to different impressions imposed on them. It can't see any pushing force. And so just explaining that if you take a proton, an electron, and a proton, a deuteron, I think they call them, something like that. Anyway, you put those together and you create a very compact mechanism because of the way they attract and hide each other from each other, kind of thing. So two protons don't need a strong force to be pushed together. All they need is an electron to be shoved between them, and there won't be any problem with the protons getting very close. I mean, that's one of these decisive little statements that, it's the speed of force. These are the little bits that you have to understand, that you don't need a strong pushing force if you don't have any force to overcome. And the fact that electrons and protons inversely change the universe means that they can get very close to each other. Character of the momentum causing force. So that's it, just simple. And all of physics. So I'm just pointing out it's the 2 plus 2 plus 2. There's two kinds of force, plus and minus force, electron force, proton force, however you want to distinguish it, green versus red. There's two kinds of matter, green versus red, or plus versus minus, or north versus south, or however you want to distinguish it, proton versus electron. And there's two kinds of interactions. The object is the proton or electron collects the force and is moved by it, gains momentum, shares its momentum, or it reflects. And that's it. Or passes through and changes color. Sorry, that's the other one. I guess that's 3 technically, right? It sticks. Well, the sticking rule is just one rule. It sticks unless it's going the opposite way. If it's heading right towards you, then you throw something at it. What you'll do is stop it. You won't reverse it. So you have to go through stop before you can go reverse. One of those kind of things. The black in the center. So it's two different bullseyes. They're just showing that magnetism's a little more complicated than just saying one end is proton and one end is electron. It's a little more complicated. It's the pattern that's different. So one end is a bullseye with a black center, and one of them is a bullseye with a red center. And it's the pattern that's different coming out of the north end and the pattern coming out of the south end. And there's just the same rules. When the patterns match, there's repulsion. When it's the same pattern on the same pattern, they repel. When it's opposite patterns, they attract. So till the draft book. Okay, so that was chapter 2. And then there's chapter 3 on atoms. So we'll do a little bit of that. South poles. And we thought of this as a north pole magnet in between two. So just pointing out that if you took magnets and you put them under, between a pane of glass, little round magnets, and you face them, north, 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 north for the electrons and south, 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 south for the protons, that you could create arrangements underneath that glass that would be durable. That is, the magnets wouldn't just flip and turn and attract each other. That instead, the north-facing ones would all repel each other, and they'd all be attracted to maybe a south-facing magnet in the center. And you could actually create arrangements where, even though the magnet wants to go to the center, it can't because of the pushing pressure against the other north-facing magnets. So you could create arrangements where they're locked, magnetically locked. Now they can do that with superconductors and all that stuff because it doesn't have all this atmosphere and it doesn't allow things to flip and all this kind of crap. So that's the big difference. if you have a monopole, a true monopole, and that's what the electron and the protons are, is true monopoles, they're not dipoles. Then it's easy because they don't flip. So it's easy to imagine what would happen.
Different planes. So in the 3 dimensions.
So I'm surprised, sort of, that no physicist really goes into understanding the elements, the positive, the negative, the proton and the electron, as the same polarity that creates magnetism. They are the magnetic monopoles. It just seems quite obvious that magnetism and electricity are being created by the same elemental bits. It's just that the shape or configuration is different. I mean, technically electricity isn't a force. It's just the magnetic force, the charge force, if you want to say that. The force that affects electrons and protons. And all you're doing is changing a pattern of that force based on the structure of the atom and how the polarity is viewed when they're doing the group behavior thing. The school of fish is very different shape than the fish.
Now, the geometry can get bigger and bigger.
So yeah, you can just go with this simple geometry argument that the reason why there's a limited number of possible atomic configurations of nucleuses is because it's all geometry. You're going from a triangle to a square to a pentagon to an octagon, blah blah blah. And that's the limitation, is how far away from the proton the electrons are getting, because once they get a certain distance from the nucleus, they're not going to feel it anymore. It doesn't have enough charge to reach those distant locations, and that's the size limitation. And so there's only a certain number of arrangements that are very stable, where that create equal potential between the pressure of the objects in the arrangement, and there needs to be equal pressure to sustain its shape, to sustain its structure. One of these electrons, if I made a triangle of electrons around something, you could sort of understand that they could all be an equilateral triangle. They'd have equal pressure and distance between each other, and if I changed that in some way, I would create vulnerability to one of the magnets finding a weakness in the pressure and therefore crashing into the proton, the positive nucleus.
That, and so I'll erase and see if there's anything else I need to point out.
Well, that's not very helpful, but thank you for doing that.
Moving.
Alright, so just pointing out that the nucleus viewed from different locations is going to look positive if it's got a big fat proton in front of you, right? And the electrons are over here, then it's going to look positive. But if you're looking at, and the electrons here and the protons over here, it's going to look negative. So everything has a pole, more than one polar circumstance. There's poles going in more than one direction. So it's not as simple as a dipole. It's a tripole, quadpole, all that kind of stuff. Continuing.
They're still durable because they've been cleaned of.
So yes, the whole point is these atoms, the nuclei, are created in the suns. The suns create the nucleuses, and they're squeezed essentially. The high pressure of the sun squeezes everything together, and it kind of spurts out all of the error code. So the geometry is very pure, and there's no irregularities, and blah 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 blah. And that's why the things are durable. It's because they were made under very high pressure, and they're very pure. That's almost like creating a diamond. You create a diamond by taking the carbon and kind of crushing all the nonsense, any impurities, other stuff. The heat and the pressure pushes all the crap out essentially, and you're just left with those elements. And so it's it's the lack of impurities that make it transparent, you could argue, because the geometry is so regular and so perfect. Alright, something like that anyway. Seems quite reasonable to me. Alright, so there was a couple of other videos I did, so I figured it's good to mention them in a YouTube video. So this Stephen Wolfram guy, physics prodigy kind of thing, I guess is his, he does this computational stuff. He has some Wolfram language or something he's very proud of. Whatever. He knows a lot of stuff, no doubt about it, and so he decides to talk, shit. It's very nice. I mean, he does more than one kind of, on different subjects. I mean, he's a capitalist, and so he talks about his little making businesses things, and does lectures on different subjects, but he spends, a couple hours a week answering different kinds of questions about physics. And so, bravo for interacting. I really hate that idea, though, of just answering these standard questions and you get to pick which questions you answer and all that kind of crap, and there's no back and forth and there's no scrutiny of anything said, so in those senses it's all kind of fail. I mean, it'd be much better if he had a conversation with somebody who disagrees with him. Frankly, I mean, that's the way the conversation should take place. It shouldn't be among people who agree. It should be among people who don't agree. But anyway, two videos I did so far. So there's like 160 of these, hour to 2 hour videos, and talking about a lot of different subjects, and you have to go through them all to try to find little bits that might be of interest in terms of being elemental physics, because the rest is just talk about mathematics and some other mush, and they're not terribly relevant questions, like how long would you live if you fell on Mars or some kind of crap like that. I mean, all this, the really, well, anyway, it's either way too scientific, like they get into what half charge does a half quark have, or some kind of bullshit. It's either way too lost in the bullshit, just so abstract a subject, or it's just, whatever. Homer Simpson kind of stupid questions. So anyway, play a little of this. And if I want to measure it as it's absorbing the force, I can measure the incremental change in its velocity. Right, so this is the F equals ma crap. So he did the same resuscitation that we've heard over and over, that Newton said F equals ma. Newton didn't say that. Newton pretty explicitly said any change in force, any force that affects you, is going to completely be represented by how your momentum changes. So the part of the force that you absorb or you're impacted by will show you, its presence by changing your momentum. And time is only used if you want to know the rate the force is changing you. Then sure, divide by a second or divide by 10 seconds. But if you don't want to know the rate and you just want to know the total force, you just look at your total change in your momentum, and it gives you the answer. That's Newton's physics. They keep, frankly, I mean, it's not that hard to find out if Newton said any of this crap, right? So he didn't say it. They keep saying he said it. It's not his formalization. It's not his math. It's not his perspective. It's not his terminology. He didn't say, he didn't notate. 9.8 meters per second. He didn't notate that as second squared, because it's not second squared. Something that happens at a regular interval, you don't automatically square it. Squaring doesn't account for it could be affected 10 times, it could be affected 100 times. I mean, you don't, say if Mike Tyson punches a guy, and he tends to punch once, or averages one punch per second, you don't just say, well, I'm going to do punch squared. No, you're not squaring the punch. That's not the right way to do it. You have to count how many punches there were and multiply by how many punches there were. You don't square the punches. All right.
Skateboarding. Then if you jump off your skateboard.
All right, so then he's just doing this, again, to me, a typical mistake in talking about an equal reaction force, that Newton's third law implies the existence of some opposite force that acts when any force acts, and that's not what's taking place. You're giving your force away. You're pushing, you're throwing some part of you in a direction, and to throw it in that direction, you're essentially imbalancing the rest of you, because now you've given away this way and you still have this way inside of you. So it's as simple as just saying, well, the video I'll play has it in it. Just take a balloon and you fill it full of something and you make a hole in it in the direction the stuff goes out the hole. Well, all the stuff going this way inside the balloon is still there, hitting the balloon this way. And all you've done is take away the stuff that was hitting this way, because now you've let it out. And so logically, yes, you still have this way. You don't have any opposing force to balance, because you just gave it away. So obviously this has to move this way. So you're just imbalancing the force equation inside the object. You're giving away. So if you give away your money, you got poor. Nobody came and took it from you and made you poor. The act of giving your money away made you poor. If it falls out of your pocket and you lose your quarter, there's no opposite force that says you lost a quarter. Okay, you lost it when you gave it away. Friction takes your energy. You give it to the friction, so to speak. You give it to another object. And when you give it away, you lost it. Orbit requires a perfect speed, and you can't gain that. And so I'm talking about this, this stupid model of the atom. So he's probably using that the electrons move in these blah 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 things and rotate, spinning around, and all this. Now, it's just improbable to start talking about electrons having some perfect speed to stay within the charge balance constantly in some sort of orbit. It makes absolutely no sense. First, there's no explanation for where that speed comes from, where the electron's momentum comes from, and how could it keep the same momentum for a billion years? Just totally unrealistic. The photons will be broken in their phase and they won't. Right, so all the photon experiments are really just talking about breaking the phase of a photon. You have energy coming in sequence, and then you put it out of sequence, right? Change its phase, and now it can't be seen as the same signal. You had dot, 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 nice Morse code signal, and now you have dot, dot, dot. It's broken. It can't be received, okay, by the object as the same thing. It's not the same thing. It's not going to create the same response in the object because you've broken the resident pattern. You've broken its structure. And so that's what we do to photons, is we put them through a polarizing film, or we put them through diffraction gradients or something else, and what we're doing is taking the bits of the photon and we're scattering them, disrupting their phase, and there's a 50-50 chance that you reconstruct the phase on the target. So that's what you're going to see is some kind of pattern. That's the residue of you disrupting through some mechanism, changing the phase. The polarizing film uses one technique, which is, just puts a second layer. So the first layer of plastic causes a phase change. Well, if I have two layers of plastic, then I've reversed the first phase change. Okay, so the stuff going through the two layers is back in phase. The stuff that goes through one layer is out of phase. So it's a little different than the bars. When you put the bars in, okay, what the bars are doing is deflecting the light, scattering it, and the process of scattering the light ends up doing the same thing of messing up the phase, because now the photons are traveling different distances, and inevitably some of them are going to be a half wavelength out of phase when they land, and therefore they're not going to be able to reconstruct the dot 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 pattern, and they're still going to be stuck with some sort of dot 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 pattern, and that won't be seen as a photon. I don't know how people make sense out of it, but whatever. So it's a key foundation of doing good science is you don't rely on one experiment. You say, okay, so I think this was a comment regarding an Eddington thing or something, so I don't know exactly what that was. So, I don't think we did this one yet, right? Yeah, this is Force in Motion, so this is the other one, the second video, which was Eddington and the bent light space thing. And so again, we have the generic story about Eddington, but the change is, as Wolfram admits, it's not a very good experiment, which is hilarious, because he doesn't explain why, well, that bad evidence is still good evidence. He doesn't explain why this isn't, whoa, a key problem in the fact that we've all accepted relativity as a theory, and yet we really haven't redone this critical experiment to proving a specific element that is rather extraordinary. The fact that photons would be bent twice as much as any other material object. And I have to say any other material object because no force is bent by gravity. I mean, you can't bend magnetism, you can't bend electricity, you can't bend anything else with gravity. So why the hell are we even having a conversation in terms of saying, shouldn't we have really good evidence if we're going to claim it's bent, and then it's bent twice as much? I mean, that's an extraordinary claim. Was as Einstein changed his prediction in those 3 years. And then, that's the funny part too. He points out how there was an eclipse 3 years before the one they actually did that they failed to be able to do because the World War I got in the way. And at that time, Einstein, his formula that he was arguing in defense of only had light bending the same amount as matter. That is, based on its velocity and some arbitrary establishment of a mass, I suppose, what he predicted the bending would be. And he doubled that. By 1919, his prediction was it would be twice as much. Whatever. An extraordinary kind of, like I said, it's kind of an extraordinary change. It's kind of a big difference. Twice as much bending is, it's a lot of bending, twice as much.
Ellipse, okay? But so an ellipse has sort of an elongated semi-major axis and a semi-minor axis.
Right, so this is just the discussion about Einstein's math applicable to how ellipses work and the irregularity of Mercury compared to the Earth and the other planets. But again, that irregularity can first be noted that, of course, planets extremely close to the Sun would feel irregularities that the further away planets would never feel. So that's your first argument, that any irregularity is going to be much more visible to a planet that's close than any planet that's far away. And Mercury is substantially closer to the Sun than Venus. So the pattern is sort of broken where Mercury is really close. So the simple argument could be is there's lots of irregularities in the Sun that one could imagine. We see it, we didn't even know it rotated until, I don't know, 50, 100 years ago at best. There was just speculation, because you can't see it. It's the inside that's doing it. So all those things become factors in understanding that all you need is a tiny little precession in the Sun's motion, and that would be realized in disturbing Mercury's motion, but you wouldn't see it in any disturbance in the Earth's motion, because the Earth is just too far away to see that little tiny difference. At a distance, the wobble disappears. It's a whole resolution argument. I mean, it's just, it's a solid argument. That it could, the explanation for Mercury's change is a mechanical little push. And there's lots of ways to establish a cause for that push. Coming up with the same answer.
So that was a little bit of a subtle thing to untangle. But in any case.
Okay, I can't remember exactly what the subtle thing to untangle was, but obviously Einstein's equations are incredibly complex and, again, just probably rely on creating a tiny fluctuation, and all you're doing is making it small enough that Mercury can feel it, but the Earth can't. To some indication that there, and it has something to do with the inverse squared law being converted into a cubed law. So for some percentage of the Sun's mass, they have established a cubed law rather than a squared law, And that's the little tiny difference you need to create. And if that difference existed, if at certain distances the inverse square law didn't work, then you can really understand that how planets far away would never feel it, because it's such a tiny percentage of the total energy the sun is producing, the total gravitational energy, which is actually a lack of energy, but whatever.
Innate, because there's actually photons trapped in orbit around a black hole.
Right, so there's another argument about how black holes capture photons, and that photons are bent by gravity, and that's how they get captured, and all of that stuff is theory. It's really not evidence-based arguments, and I think it has gigantic logical flaws, blah, 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 blah. Alright, so that's the update of the website videos. There was another discussion by the John Chappellers regarding the Faraday paradox, but they didn't add any value, because the guy was basically defending Weber electrodynamics as an explanation, and he was doing it based on an argument that said the experiments were exactly the opposite of what I would argue the experiments show. So, you know, like when both are spinning, there was no voltage, and that kind of, it's a complete disagreement with 99% of the evidence. So what's the point of having the argument if the real argument is we can't even agree on what the evidence shows? So if you're not going to agree what the physical phenomenon actually produces as an end result, then you can't really argue about theories until you establish what, I mean, you know, is there water in the glass or is there no water in the glass? I mean, it's a completely different theory if there's water in the glass than if there's no water in the glass. So you have to agree whether there's water in the glass first. And then you can theorize about how it got there, how it stayed there. Alright, so disappointing that, yeah, that was a waste of 2 hours. But anyway, it's an interesting subject. We'll see if they ever get anywhere regarding it, because it really is it's another source of free energy nuttery. It's you know, it's got a lot of you know, and again, it's sort of incredibly relevant to Einstein's relativity theories in the sense that he had to. It was a piece of evidence that points out that maybe his Jesus. You know, I'm trying to think of that equal word. You know, that doesn't, you can't tell that you're moving when you're moving, kind of thing. That it's all right. Let me pause and I'll try to remember. Equivalency principle. You know, that it's that all motion is equivalent and therefore it can be called relative, and it doesn't need to be connected to any absolute space and time. And this is sort of an experiment demonstrating that no, it does matter who's moving. It matters. The wire can't collect. It can't produce the same effect if it's moving versus not moving, because the physical motion is actually disturbing its atoms and making them move, and it's the motion of the atoms that are allowing for the induction, that kind of thing. So it matters whether the magnet's moving or the wire is moving. It makes a difference, especially when the motion is fast, because that changes the atomic structure of the object. When you're moving, you are physically different than when you're not moving in absolute space. So a wrench on Earth and a wrench hurling towards Alpha Centauri or something, if you could, you know, if you could see exactly where all its electrons and protons were and what direction vector they had, you'd see that the two images are not the same. That the wrench that's moving is physically different than the wrench that's not moving. Alright, so we'll move on to the silly video and then do comments. Alright, back. Alright, so this is some channel called funsciencedemos. A force is a push or pull. I mean, the title's not even good grammar, and yet it's supposed to be an educational video. It's just, for kids kind of thing, I guess. But just so bad. So let's, it'd be great, just to see a physicist explain how there can be anything other than pushes in the universe. Just say, okay, there's two things separated by empty space. How can I interact with the other thing? I mean, aside from throwing something at him, okay, pushing on him with an object I throw, there's nothing you could do. You have to throw something. There's no simple, elemental, basic mechanism that could possibly create some kind of pull. All right? I mean, pull requires you to, reach out and pull, okay? Which means reach out and push on the back side of something. I mean, it's just so obvious. It's got to be a push universe. It's the only rational way to look at things. It's just so disappointing that physics doesn't go anywhere near the subject, and it's so elemental, it's so fundamental to how you understand mechanical things. I mean, there is no mechanically simple pull. It's just, there's no such thing.
Hi, I'm Jared. Welcome to Fun Science Demos. The big idea.
Okay, I got sped up because this guy's such an annoying jerk. I don't know what this alcohol crap is on the bottom of the screen. Why the fuck are you doing that?
The idea today is that a force is a push or a pull. Through science, we've discovered that if I give a little push, a little force is created. And if
Oh, duh. So science figured that out, huh? Oh, God, too stupid. So, I mean, it doesn't really get into the subject of push or pull, right? So he's not going to show me how, hey, I can do something really simple and pull the object. No, I can't do anything simple and pull the object. I have to do something complicated to create something that looks like a pull. But it won't be a pull because I'll be pushing on it. Yeah, so no matter, he could just show how, look, if I push on it, if I pull it towards me, what am I going to do? I'm going to apply a friction force to it that's going to be in the opposite direction, blah, 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 blah. Obviously, I'm not pulling it, I'm pushing it.
if I give a big push, a big force is created. But it's not just us who can do the pushing and the pulling and create the force. Lots of other things can create.
So the pushing and the pulling would be a sensible thing to say. Look, there's an electron in space and it moves here and then it moves back here. Well, what's hitting that electron? Microwaves, all kinds of energy is hitting that electron. And all that energy is going to be changed by that motion because of the Doppler effect. So just using the energy you know exists, the photons and all the other crap you know already exist, you can figure out that I'm going to change what's going on, right? There's a photon coming towards my hand. I am blue shifting it by moving into it. Okay, you can't see the blue shift, but it's there. I have, in fact, blue shifted the light. All right, and if I go backwards, I'm red shifting the light. And if I can move my hand fast enough, you'd see it. Because it's happening.
The force. Like air. So take a look at this. I'm going to put some air in this balloon, and that air is going to have a force. Then we can have some...
Oh yeah, right. And it's what's the real force? What are you really doing though when you put air in the balloon? Okay, you're just putting the same atmosphere that's on the outside on the inside at a higher pressure, which means it's pushing on all sides of the balloon. And then what are you going to do? You're going to let the stuff going one way out. So the pressure going one way that would hit the balloon isn't going to hit the balloon. It's going to fly out of the hole in the balloon. That's the right way to explain it.
fun with it. So the air is exerting a pressure on the balloon. I'm going to put it against it.
So the air is exerting a pressure on the balloon. It just doesn't even, he's not even saying anything, right? Right? I mean, there's air in the air and there's air in the balloon. You're supposed to point out how the two airs are different. That somehow the air in the balloon is denser air. There's more air in the balloon than there isn't than there is on the outside.
Table. What do you think is going to happen? I think the air is going to exert a force that's going to push down on the table.
All right, so he's saying it exactly physically wrong, right? Because we all know it doesn't make any difference whether the table's there or the table's not there. The balloon is going to do its thing, okay? What the table does, what the dust does, all this other crap is completely superfluous. Doesn't mean a thing to the balloon. All the balloon cares about is, I got rid of stuff going this way. So it works in space. It's not going to push. In space, the balloon goes just as well. Because there's no air pressure, so obviously it's not going to go just as well. But obviously, it just can't make any difference to the balloon. The balloon's just losing pressure in a direction, and that's all that's going to matter to the balloon. Whether there's something to push on or not push on doesn't make any difference. That's the real physics. So this has got 500,000 views, and it's talking shit. It's not good physics.
What happens when it pushes on the table? The table's
Pushing on the table. No, it's not pushing on the table. So wrong, 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 wrong.
too heavy to go anywhere, but the balloon's light enough to take off.
The balloon's light enough to take off, right? Did the balloon take off because it was light? No. Okay, it took off because you allowed a bunch of its energy going in a direction to escape. And it was left with energy still going this way, still pushing on the inside of the balloon in the opposite direction, so it kept going in that direction.
It almost looked like a jet taking off. In fact, that's how jets move forward. That's not how they fly. They use their wings to fly, but...
Oh, so how they fly. It's just hilarious. No, it's actually the jet is how they fly. You don't need the wings except for to stabilize. Because it's where you point it is where it's going to go. It's where you point it. It's where the nozzle is pointed. It's going to force the matter to go where the opposite direction to the nozzle, because the nozzle is basically saying, I'm giving away this way. Well, then I have to have that way.
jet engines, they take air in and force that air out with a lot of pressure, causing the jet to move forward. Kind of like what we're about to show you.
All right. So at least that part wasn't completely wrong, right? Because yes, they're moving forward because they're pushing, they're getting rid of force in a direction.
Check this out. So I strung a fishing line across the room and I have this little straw slider threaded right through it. I'm going to attach a balloon, fill that balloon with air, let it go and see what happens.
Yeah, so you don't need the string, you don't need the straw, you don't need any of that. You just did that experiment. You shot the balloon straight up. So now he's going to point out there's no pushing. The balloon will not push on anything. It's not going to be pushing on something to go somewhere. It's going to be letting go of a push.
So now I have the balloon.
An internal push. So there's a bunch of stuff going left, and there's a bunch of stuff going right in the balloon right now. And when he lets his fingers go, he's going to let the stuff going right free, and the stuff going left is still hitting the other side. And so yes, it's going to go the direction where it's getting hit more times, where it's being pushed more. It won't be pushed in the right hand direction because his hand's not going to be there, and there's going to be a hole there, and the energy is going to go right through the hole. But he's still going to be pushed left, and that's how it really works.
Balloon attached to the straw, and I have air under pressure in the balloon. I just need to move the camera so that you can see the whole launch. So we're cleared for takeoff. 3, 2, 1. So what happened there? Well, when I let the balloon go, as I was holding it on the table, the air was pushing against the table.
Oh, just, ow, 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 ow. I mean, it's just so wrong. I wonder if anybody in the comment section just says, that's so wrong. Why did you do that? It's really stupid. Let's see. 5 forces and I'm converted in the next month. My fault for not looking ahead in the curriculum. I showed this video as an introduction to forces in a grade 3 class. I had one student has been confused ever since, as air is not one of the 5 forces we then covered over the next month. So there aren't 5 forces. There's only one force in the universe. It's all the same stuff. Okay. My fault, though, for not looking ahead in the curriculum. So he thinks that's what confused the kid. So only one kid was confused. And he basically just told them, you need to push off a surface to go. You can't go without pushing on some other surface. Oh, shit. Your Simply rule. I am using this ARVU with some deaf kids. So they already got it bad. They're deaf. And now you're going to make them stupid. Dumb. This was great. Homeschooling my kindergartner. So great. So this is not good news for the human race. Okay. Magnetism aside, which nobody honestly claims to understand, can you provide a practical example of a pulling force creating motion and acceleration? So that would be good. Yes, can you show a real example of you pulling on something that doesn't involve pushing on something? Anyway. So yeah, so nobody just points out, oh wow, you really made a mess out of that. The table's irrelevant. The balloon goes because the balloon's net force changes. The net force inside the balloon changes. That's why the balloon goes. You're an idiot.
When I let the balloon go here, air was actually pushing against air. That's what moved the balloon forward.
He says it again. So now he's saying the balloon pushed against the table, and now he's saying I need the atmosphere or the balloon won't go. So the thrusters don't work in space because, see, without any air to push on, the little air, they actually use air, you know, to push things around in space. So, you know, they use any kind of molecules. It doesn't matter what they are. Anything will work, heat, anything. So they just create something to let go. They let go of something going that way, and when they let go of it, when they allow it to exit from their material connected atomic bits, their net atomic bits obviously have less energy going. You know, they have less energy hitting them on their you could think of it like an atom, and it has a membrane. The inside of their membrane is now lost, you know, energy in one direction, and it still has energy in the opposite direction. So it has to go in the opposite direction. No air to push on required. So he's not even getting this push-pull thing. He thinks that motion is a byproduct of you pushing against some kind of friction or pushing against some sort of other object. And the point is that is the concept of transferring energy anything other than pushing on something? Nothing pulls on something.
Forces. A force is a push or a pull. Air
Now, it's not a pull. You're not going to show a pull. So again, more bullshit.
can push.
Okay, air doesn't push. Air releases energy, and it just doesn't matter where it goes. Now, obviously, you could take something and you could shoot the energy out, and then it could. It's like I could throw a rock at the moon, and I could go into its gravity at just the right velocity, and the rock would come back and hit me in the face. So obviously, there's a circumstance where you can send energy out and then have it come back and push you some more. So you could gain a little extra velocity because you have a reflective surface, and that reflective surface will push the energy back. But in most cases, the object is going to leave before the reflection is going to get to it.
Science is cool. Thanks for watching. Don't forget to check out our links in our...
Science is cool. This wasn't science because it was done badly. Yeah. All right. Oh, look, he has a lever in this other video. I don't know whether I should. Do I have the? Can I really stand watching it? All right, maybe I'll click on that, and we'll see how bad that is. It's a lever with balloons. All right. So that's for some other time. So just a horrible piece of crap video. All right. So now we'll see if we can find a comment or two. Alright, so we have this stupid. So there's the video Faraday's paradox and unipolar induction is the subject, okay? And it's, you know, it's a lot to the subject. It's a subject all of its own. And this guy posts hashtag Faraday shield. How is that a response to the Faraday paradox? They're two different subjects. The fact that you can stick a lightning rod next to you, okay, and a lightning rod will catch the lightning, okay? I mean, if you want a shield against getting struck by lightning, you just carry around a lightning rod that you can stick into the ground all the time. You know, it's well grounded. You know, that has a bunch of little pieces of metal that touch the ground and makes very good ground contact. Well, then you're never going to get hit by lightning. All right, so Faraday's shield isn't all that complicated. It's just a big sink, okay, that makes it easy for, because and we know the electricity is traveling through atmosphere. So without an atmosphere, you don't need a Faraday cage, because you're not going to get struck by lightning. You're not going to get struck by an electrical potential, okay? It's not going to happen. So, I mean, there's nothing magic about a Faraday shield or a Faraday cage. It's just this obvious, it's a lightning rod. And yeah, you have to have the rod in little bars going in all kinds of directions to make sure none of the electricity can get to you. But that's all there is. It's just putting a ground around you, okay? And it doesn't have to be perfect, because the ionization of the atmosphere can bend. Ionization atoms can bend in different directions. So there's no problem with deflecting the lightning into the metal instead of deflecting it, having it hit you. So that's not even complicated, that subject. I mean, so, what is this, though? What is this as a fucking response to anybody anywhere on the internet? I'm just going to hashtag the subject. It's not the same subject. It's not an appropriate reference. It doesn't mean anything. What the fuck is it? What am I supposed to take from that? How is it useful as a comment? I mean, it's so obnoxious. It's just like saying, I could post a comment on anybody's video and I could just say happy, happy, good, good. So what? Yeah, and people read and go, what the fuck does that mean? So you got people distracted and you got them saying, what the fuck does happy, happy, good, good have to do with changing a tire on a car or something? What the hell was that guy trying to say? So yeah, you can cause a lot of fucking noise. Shit. It's just so disappointing. Alright, alright, but so this video was web videos and comments. Okay, so it was just an update video. So the guy sits there and says, alright, but you're wrong about UFOs. I mean, oh yeah, and you think because you say so, I'm scared that there's really some credible evidence? No, sorry. Watch the Stan Friedman lecture. He was good. Apparently he got abducted by aliens, is now gone. So he was good. He's not good anymore. Shit, he didn't use his alien technology to live longer or any of that stuff, or, whatever. Shot himself with the dematerialization gun that he stole from the UFOs. I mean, what's the fucking story? But I mean, god damn it. Too stupid. God, I hate this planet. Question. I am a philosophy major and always been trash at anything involving memorization. Well, likewise. So physics, bio, and anatomy, all that isn't my thing. Well, I don't think you have to memorize everything in any of those subjects. You can just write the formulas down and you can look at them when you need to. I mean, you can cheat. But some stuff is, it's pretty hard not to memorize. 9.8 meters per second, yeah, it's hard not to memorize. So I've never been good at physics. So that's your excuse for not being good at it. I imagine you're not good at it because you really haven't spent much time thinking about it. I mean, you really have to spend some time with a pencil and paper and try to draw it physically to understand how weird physics is. Any playlist of yours you'd recommend for someone who has a little knowledge of physics and wishes to get a basic understanding first? Well, the book videos will do that. But I have other videos. I mean, I have the other website that I do point to now and then. So there's places you can find my preferential argument, but you might just go overview videos. So if you type in the word, draft science and the word overview, you might get the overview videos. It might be good ones to listen to. Alright, if you do make an audio book, I highly recommend putting it on a playlist for easier viewing if it's going to be on YouTube. I don't know how that makes it easier to view, but whatever. Yes, obviously I will place a reference to the location of the individual chapters of the book, and I will probably take all the videos and combine them into one video. Alright, it sounds like you're going to make it in parts. Yes, you can't write the book in, like you have to do it a word at a time. Yeah, that's the way it works. Though mad respect if you compile and edit it into a formatted audiobook. Yes, eventually. But obviously the point that needs to be done is that each chapter needs refinement. I'm doing it in this draft mode first, and then I have to be more precise in how I say everything to make a proper audiobook. But even done sloppy, it should get the point across. Though, as you've said, it's a lot of work, and most people just eat things up, so why make it all pretty when you can just say what you know, believe? Yeah, well, frankly, anybody who's going to do something rational in terms of, they interact with the world in a rational way, already knows that this isn't a beauty contest. That's not really what you're after. So, obviously. Alright, so I already took care of this dirty garage guy. Let's see. This side. What the hell is this guy talking about? Considering that one side of membrane is everything. Okay, I think I read that in another video and just marveled at how incomprehensible it was. So, to Bexar thought video, so whatever. So that's one of the videos in the contest that, who knows when they're going to get around to finally picking the winners. And I have no just from what the channel is, this Theory of Everything channel is just producing such cruddy little clips. Yeah, they really think consciousness is some sort of wooey bent space bullshit. I mean, they really think the brain isn't just some sort of computer, with neurons that are taking the place of the bits, and that it's just a cause and effect mechanical device. It doesn't do anything magical, but they think otherwise. Well, whatever. I'm just so depressing. Yeah, so this Moore guy is really way off. I mean, he's bringing up the doom, gloom, and boom channel here. I don't see any point in doing that. I mean, he just can't stay on the subject, I guess. Can't be on the subject. Alright. So, no point in going a month back, right? Because I probably already read that crap. So, just very little. So, there's obviously no brilliant counter arguments have been posted in the comments section. No links to any videos that debunk anything I'm saying. Nothing. Absolutely nothing in the form of some kind of reasoned explanation for why I am incorrect in anything I've said. Okay, that's the status of things. Alright, let's see if we can find a web. Good news. We actually have a new comment. Yeah, just in. No point repeating Eddington's experiment. No, there's a clear point to doing it, okay? It'll demonstrate that it's all a fake, that there really isn't any bending of light by the gravitational force. That if you want to bend light, you have to scatter light, and then it'll bend in any direction you want it to. But without scatter, there's no bending. Alright. The light has to hit something and be deflected by it. It can't be bent by any mechanism. Alright, that would be demonstrated if they repeat the stinking experiment. It really needs to be repeated. Okay, Dr. Edward Dowdy, Jr. Okay, unfortunately he died 2 years ago, I think. So he was a NASA engineer for 20-some years. Worked in lasers and other stuff, they shot into space. So was perfectly aware of what data they had on how light is affected by gravitational objects, and he made the direct statement that NASA has no evidence of light bending outside the lamb of the sun. So one radius, extra distance, to get outside the corona is what I would say. outside the atmosphere of the sun, the highly charged particle atmosphere of the sun. We know there's highly charged particles all the way out here at Earth. Okay, the Earth is getting hit by a bunch of sun debris. Okay, so a bunch of plasma being shot off of the sun. So we know the sun's atmosphere, goes millions of miles, theoretically. That it's not, the space between us and the sun is a lot dirtier than the space between us and Venus. I mean, us and Jupiter. And the space between Jupiter and Neptune is a lot cleaner than this. The further away you get from the sun, the cleaner the space gets, the less debris in it. I mean, these are basic little facts. The physicists don't deal with any of this. This subject will not be covered by a physicist. All right, so this is just not, I don't think this is an accurate statement. All right, I've watched all the Edward Dowdy Jr. videos, and he doesn't say he falsifies his gravitational lensing. That's not the point. The point is there's no evidence that with all of NASA's resources, there's no physical experimental evidence of light being bent. The experiments don't show it happening. That's his point. All right, there's no confirming evidence. He doesn't have decisive falsifying evidence. All right. Falsified gravitational lensing already with lasers, microwaves, and telescopes. So again, he didn't falsify. He didn't show that it's not bent. He showed that there's no evidence that it is bent. And so you have to be a little more careful, frankly, in my opinion. So unless you can show me him stating where he proved there is no bending, it's a very different thing to prove there is no bending than to prove there's no evidence of bending. Okay, there's no confirming evidence, because you have to do the specific experiment. If you don't do the specific experiment, the information you're gleaning isn't good enough to make the assertion. So obviously, there's no way for Mr. Dowdy to do an experiment where he shot a laser beam past the sun and then saw how much it was deflected, okay, on the other side. He can't do that. So he can't create evidence proving it doesn't happen. You can only show evidence that there's no experiment that does show it happening. All right. So their explanation for Mercury precession is that the sun is dragging space-time, whatever that means. I think what they're saying is that it's compressing space in some sort of local way, not in some sort of everywhere way. And yes, the whole thing sounds rather nonsensical. How can one thing be in compressed space and then something else can't see that the space has been compressed? Of course it could see that it's compressed. This effect is called frame dragging and is proportional to the angular momentum of the object. Whatever. I don't know how the angular momentum could mean anything to anybody, but fine. I don't know how they distinguish it from the magnetic field. I mean, angular momentum is the same as momentum. I mean, it's the same as a velocity in a vector. And all you're saying is there's some force causing it to remain circular. I mean, either you have to have a gravitational force push something into an orbit, or you have to use a mechanical, thrusters to push you into an orbit, or there has to be a mechanical frame that forces you into an orbit. There has to be some force applied. Even if you're a runner on a track, you have to apply more friction to turn. Damn it. Anyway. And it's proportionally angular. I don't know how they distinguish it from magnetic field. I mean, it's just, again, you can go into all these arguments about the magnetic field traps, in the sense of it causes changes in ionization. And how do you change ionization? Well, first you have to have ions. It seems that they are saying is magnetism and gravity combined effect creates a torque. Well, they're two separate effects, and obviously I would argue the magnetic effect is very slight. I don't know exactly how magnetic Mercury is, so But clearly, it can be the cause. Okay, the fact that just like with Earth, the geographic north isn't the same as the magnetic north. And if the sun was likewise possessed in the sense that it's the alignment through its center of gravity, its magnetic center is different than its gravitational center, then obvious Mercury could be picking that up, and that would explain why it's an inverse cubed law instead of inverse squared law for some portion, because the dipole field could be a cubed field. But magnetism could have been easily added to Newton's gravity. Yes, you could add a lot to Newton's. Again, Newton's theory was the sun is in this location, period. Okay, and it never moves. Okay, that's the Newton's math. And all you have to do is move that sun just a little bit. Okay, and Newton's math changes. All right, and it's going to change a lot more for Mercury than it's going to change for any of the other planets. Again, just a tiny movement in the sun's, a tiny jitter in the sun's center of gravity is enough to account for the tiny difference in the fact that Mercury has a precession issue. All right, but magnetism could be easily added to Newton's gravity just as it is in relativity. Right, so if that's all that Einstein did was shove in the magnetic field effect, if that's all his tensors and all this complex math is doing, then yeah, clearly you could have done that to Newton's equations and added some other variable. So adding another variable, yeah, obviously that's going to make it possible for you to change Mercury's circumstance. And all you're looking for is a variable you can change that affects Mercury but doesn't affect Venus. So you're just trying to change a variable that doesn't have very good durability in traveling distance. Because the inverse square is still true, according to them, magnetism shift effects of gravity, whatever that means. So I'm wondering what exactly about gravity. Something. Then he posts a link to essentially some sort of Wikipedia, Google page or whatever, and it's frame dragging about pulsars. So this is more about what they see in the observable big universe and not so much about Mercury's precession. But it's still, I guess, relevant in terms of a theoretical cause for changes. All right, so that's it. So that be enough. Thanks for the comments. I say neither one of them was a totally on the subject, but close enough. And such. So we'll call it a video. I didn't have to draw anything. I found a bunch of new dry erase pens in the garbage, so I shouldn't have a problem drawing. Lots of choices now. They'll half work, but hey, for free, I can't complain. I was almost out of crayons. So, good news. Proper ones. Yeah, these gel things were pretty good, I have to concede. There's like a solid, instead of the dry erase crap, it's like a solid crayon-y thing. But see, I have barely anything left here. And I have to say they work pretty well. But we'll back to the liquid kind, and we'll see how that goes. Blah, blah, blah. Anyway. Anything else to report on? I think so. Don't know, did I comb my hair? I don't know. I don't remember. So. Yeah, that's enough. Alright, so till the next time and such, this has been draftphysics.com, debatephysics.com also, but we need a human being capable of, with some knowledge of the physical experiments and the reason why physics believes what it believes and says what it says, and can argue that evidence and argue why the standard model is reasonably coherent. Yeah, because I don't see it. No chance. So anyway, till the next time, such, so forth and whatnot.